This is the 777X, Boeing's most advanced twin-jet widebody, which claims to be almost 15% more efficient than its predecessor. And this is the Airbus A330neo, which is almost 12% more efficient than its predecessor, the Airbus A330. But did you notice something strange? Despite these marketing claims of being significantly more efficient than their predecessors, nearly every meaningful efficiency gain has come from the same place: the engines. And not just that. Since the dawn of commercial aviation nearly 100 years ago, the industry had accepted a painful truth. The tube and wing design was the only commercially viable design, and there was no other way around it. Then in 2019, a Dutch university and KLM unveiled an aircraft called the Flying V, a radical design that blends the fuselage, wings, and fuel tanks into a single continuous lifting body. The concept promised to burn 20% less fuel than an Airbus A350 while carrying almost 350 passengers. And by all logic, it should have been the future. But 6 years later, the Flying V remains little more than a research project, with no full-scale demonstrator and no firm timeline to speak of. Meanwhile, roughly 4,000 miles away, a California startup called JetZero has moved from founding in 2021 to a $235 million US Air Force contract and a $4.7 billion factory already underway in North Carolina. And this isn't some random startup gambling on hype. In fact, JetZero's early simulations have shown efficiency gains of between 30 and 50% from the airframe alone, and more surprisingly, JetZero has locked in pre-orders from United and Alaska Airlines and intends to unveil the full-scale prototype by 2027. But here is the question. If this shape is so much better, why hasn't Boeing or Airbus built one already? And more importantly, how is a startup that's barely 5 years old building such a radical design? Well, the answer is so genius that it will change the entire dynamics of how these new aircraft are gonna be built. This is the story of JetZero's blended wing body, the design that could finally end the age of the tube and wing. But this radical blended ring design isn't a new concept. In fact, in 1947, as the jet age was just beginning to dawn, Northrop attempted the near impossible: a tailless flying wing bomber called the YB-49. While the aircraft covered vast distances with dramatically less drag than conventional bombers, this experimental jet suffered a fatal crash during a test flight, killing everyone on board, including Captain Glenn Edwards, the man Edwards Air Force Base is named after. As a result, the program lost the political battle to conventional bomber designs and was infamously scrapped. But the pursuit of blended wing design didn't stop there. In 1988, NASA's Langley Research Center initiated a foundational study that would fundamentally change the trajectory of modern commercial aviation. Recognizing that the traditional tube and wing design was approaching its absolute limit of aerodynamic efficiency, NASA challenged the aerospace industry to develop an entirely new class of blended wing subsonic transport aircraft capable of carrying 800 passengers while cruising at Mach 0.85. While the research successfully demonstrated that a blended wing body was aerodynamically superior to a traditional tube and wing design, it failed to reach the assembly line due to two main reasons. The first was a structural paradox. You see, composite material technology of the 90s was simply not advanced enough to build a flat fuselage that wouldn't crack and suffer structural failure after repeated flight cycles. And the second was airport infrastructure, which prevented aircraft with massive wingspans from physically fitting into existing gates, taxiways, and maintenance hangars. By all logic, that should have been the end of the story. Then, in 2015, a master's student named Justus Bonad at the Technical University of Berlin put forward a thesis that reopened the question entirely. His thesis proposed a V-shaped lifting body that eliminated the conventional fuselage, folding the cabin into two long angled arms. The simulations showed something the industry had assumed was impossible. A passenger jet could merge fuselage and wing into a single lifting surface while keeping the same wingspan as an Airbus A350, which meant no changes to airport infrastructure at all. So in 2019, TU Delft, the largest university in the Netherlands, partnered with KLM and Airbus to begin the long academic journey of turning that theory into testable hardware. The goal was to build an aircraft known as the Flying V, a design that distributed the cabin, cargo hold, and fuel tank across two angled arms. Beyond the radical shape, the design placed high bypass turbofan engines at the rear of those arms, producing a significantly quieter cabin and cleaner airflow over the wings. Fuel would sit distributed through the wings and the central body, reducing bending loads on the structure and delivering an airframe that is roughly 20% lighter. But despite those promising results, KLM seems to be in no hurry. Rather, it plans to take a slow and academically rigorous path, with entry into service not expected until the mid-2040s. This is where a California-based startup called JetZero comes into the picture, with a fundamentally different approach. Rather than an angular V, JetZero chose a blended wing-body design resembling a manta ray, smoother and more integrated than the Flying V's sharp angles. Now, the shape is only half of the contrast. Just 2 years after JetZero was founded in 2021, the company announced a $4.7 billion investment in a factory in North Carolina near Piedmont Triad Airport, creating approximately 14,500 jobs, with the full-scale prototype planned for mid-2027. But here is the question. Why would a startup like JetZero bother building something this radical instead of a proven tube-and-body design? Well, look at how airliners have actually improved over the last few decades, and one pattern stands out immediately. Nearly every meaningful efficiency gain has come from the same place: the engines. For instance, when Boeing and Airbus updated their decades-old 737 and A320, they didn't completely redesign the airframe. Instead, they hung new engines on the existing airframes and called them the 737 MAX and the A320neo, picking up roughly 14 to 15% in efficiency. And even if you look at the newer 777X, which is set to enter service in mid-2027, the biggest difference you'd notice, once again, are the engines. But by comparison, efficiency gains from the airframe haven't been so great. If you look at, for example, the brand new all-composite Airbus A350 flying with Rolls-Royce Trent XWB engines is only about 2 to 3% more efficient than the older A330neo, which carries nearly identical Trent 7000 engines on an aluminum fuselage descended from the 50-year-old A300. This is exactly the gap JetZero is trying to exploit. By moving the efficiency problem out of the engines and into the shape of the aircraft itself, JetZero expects the blended wing body to deliver somewhere between 30 and 50% in efficiency gains from the airframe alone. And building that airframe first, before Boeing or Airbus commit to one, would hand JetZero a first-mover advantage that simply hasn't existed in conventional aircraft design for decades. But that raises another question. If the blended wing body is so much better, why aren't legacy manufacturers like Boeing and Airbus already building one? Well, for the same reason NASA walked away in the late 1980s. You see, airport gates today are designed around the relatively long and narrow airliners we all know, but a blended wing body is the opposite of that. Shorter at the front and much wider at the rear, which can push the aircraft beyond the footprint a standard gate was built for. But JetZero plans to solve this by introducing folding wings on the eventual production model, similar to the ones on the newer 777X, though the current prototype doesn't have them. The second obstacle, as we mentioned earlier, is pressurization. Conventional airliners settled on the tube-shaped fuselage long before pressurization even mattered. But it turns out that the tube shape is an ideal choice if you want to pressurize it. It is the same reason propane tanks, oxygen cylinders, and almost anything else built to hold pressure end up cylindrical. A blended wing body, on the other hand, has a far more irregular and complex shape. So pressurizing it demands considerably more material to resist those internal forces, hold its form, and avoid developing fatigue cracks over years of service. JetZero plans to get around this problem by building the entire aircraft out of carbon composite. But unlike Boeing and Airbus, which bake individual parts in pressurized industrial ovens, JetZero intends to use a low-temperature cure material that allows the whole airframe to be baked into one seamless structure in a single heating cycle. But that design choice, though, created a different problem, one that could have crippled JetZero's future before it even started. The thing is, when a fuselage is just a tube, a manufacturer can build different-sized variants of the same aircraft by simply adding or removing slices in front of and behind the wing. And that flexibility is crucial because it lets manufacturers sell one aircraft to airlines flying very different routes without designing a completely new aircraft each time. Nowhere is that clearer than the Airbus A320 family, where the A320neo is built primarily for short-haul domestic flying, while its stretched sibling, the A321XLR, serves long-haul routes with low passenger demand. But doing the same thing with a blended wing body would mean a separate production and assembly line for every variant, which not only complicates the process, but makes the entire lineup far more expensive. So how do you fix that? This is where things get interesting. In April 2001, Boeing filed a patent with Mark Page listed as one of the inventors. That patent described a passenger cabin built from rectangular sections running front to rear. Sections that could be added, removed, or swapped depending on requirements, almost like Lego bricks. And since patents expire after 20 years, this one expired in 2021, the same year JetZero was founded. JetZero now intends to use that exact approach, manufacturing sections separately and bonding them together in whatever combination a given aircraft size requires. Following these developments, United Airlines placed a conditional order for up to 200 aircraft, followed by Alaska Airlines, which came in as an early round investor. And so far, JetZero has secured $2.5 billion in verified private investment, government grants, and state incentives. Then in August of 2023, JetZero secured a contract worth $235 million from the US Air Force to build the full-scale demonstrator. The Air Force's interest comes down to versatility, since a blended wing body could carry troops and cargo, or serve as an aerial refueling tanker under a program the Air Force calls the Next Generation Air Refueling System, or NGAS. And that's because a blended wing body carries a relatively low radar signature, which would make the aircraft far less vulnerable in some key defense scenarios. But the money is only half of what makes JetZero credible. Mark Page, JetZero's chief technology officer and one of the two founders, has spent years in aircraft design at both Boeing and McDonnell Douglas. In fact, he was a central figure on that joint project between McDonnell Douglas and NASA we talked about earlier. And it isn't just him. Other key people inside the company have held important portfolios at Boeing, Airbus, Embraer, Bombardier, Safran, Rolls-Royce, and other major names in aerospace. But here is the problem. While $2.5 billion is a serious sum, it is nowhere near what it takes to design and certify a new airliner, especially one this unusual, which by some estimates would cost around $7 to $10 billion. So what exactly is JetZero's plan? You see, unlike passenger jets, which demand billions of dollars and years of rigorous certification, military aircraft face a different, less punishing process. Since the US Air Force was one of JetZero's earliest backers, the company plans to start with two military variants. The first is a straightforward transport for troops and cargo. The second, also destined for the Air Force, will most likely serve as an aerial refueling tanker. And once the program starts turning a profit, JetZero will unveil the passenger version. To keep costs down in the meantime, JetZero is leaning heavily on a commercial, off-the-shelf approach, which involves fitting components that are already flying on other aircraft rather than designing everything from scratch. For instance, the demonstrator is planned to use active side sticks from BAE Systems, the same ones already flying on Gulfstream's newest business jet, which in turn means pairing them with a flight control computer from Thales, Gulfstream's existing supplier. The aircraft is also set to use main landing gear sourced from the MD-11, avionics from Garmin, and rudder pedals, flap handles, and speed brake handles borrowed from the Gulfstream G650. Individually, these choices sound minor, but multiplied across an entire airframe, the gap between developing something from scratch and buying something already certified and flying could translate into savings worth hundreds of millions of dollars. Powering the demonstrator will be the Pratt & Whitney PW2040, an engine already flying on many Boeing 757s and the Air Force's own C-17 Globemasters. It's a 1980s design with a dual-rotor layout, and it was the first commercial engine ever equipped with FADEC, a system that manages engine performance without mechanical input from the pilot. Which raises an obvious question. Why would an aircraft entering service around 2030 fly behind an engine designed in the 1980s? If you follow aviation news closely, one thing you would instantly notice is that a major factor hurting the industry right now is the reliability and longevity of newer engines. Whether it is the Pratt & Whitney geared turbofans on the A220 family, the Trent 1000 on the 787 Dreamliner, or even the brand new GE9X on the 777X, almost every modern engine has run into serious durability problems. So JetZero believes that fitting these modern engines could prove a huge setback to the program if they end up causing reliability concerns, with the efficiency gains canceled out by extra maintenance costs and lost revenue from grounded jets. And while there is news that JetZero might eventually pivot to a modern engine, for now, the company is taking the conservative route. But there is another reason that might have played a part in this peculiar decision. The C-17 Globemasters and the military 757s flown by the US Air Force use this exact engine. And the Air Force has built an entire supply chain around the PW2000 family while planning to keep those aircraft in service for years to come. While Pratt & Whitney does have plans to offer a newer and more advanced engine for the C-17, that would be a risky move, since an engine of that unusual size has almost no other application to fall back on. Instead, Pratt & Whitney could work with JetZero and offer something far more conservative. An improved PW2000 with better electronics and refinements to the internals while maintaining the rest of the engine's configuration. And since the US Air Force is JetZero's first customer, that single engine could serve both sides of the deal, powering the JetZero Z4 production aircraft while handing the Air Force the upgrade it needs. So, what do you think? Will JetZero actually get a working demonstrator into the air by 2027? Or is this destined to become another blended wing body that never makes it past the drawing board? Let me know your thoughts in the comments, and hit like and subscribe if you liked the video.